Hello and welcome back to our next chemistry basics and atomic structure discussions. This one, N6, average atomic mass calculations. So we left off last time looking at this chart where the average of all natural occurring isotopes of that element. So for this example of carbon 12, 13, and 14, we can see that the percent in nature is not equal to each other for all three isotopes. So again, we cannot add up 12 plus 13 plus 14 and divide by 3. We get an average of 12.011, which is nowhere near how you normally do averages, just explained. So ultimately, we want to take into account how much of each isotope there is to get an accurate picture of what we're likely to scoop up. So if I had a bunch of carbon and took a scoop of it, what's the majority of it going to be? That's our goal ultimately to figure out. So we know carbon is 12.011. We know that of all that you should scoop up, the average of each individual atom is going to be 12.011. We know that each individual atom is going to weigh either 12, 13, or 14, but the average as a whole will be this. Average obviously gives you a clue as to what the most common isotope is. So again, average mass of carbon, 12.011, directly off the periodic table. Based on that idea, which one should be the most common? Now I know you know the answer, carbon 12, because you saw the most abundant on the previous chart. 98% plus was carbon 12. So calculating average mass is pretty straightforward. It basically takes into account every isotope that we know of multiplied by the abundance. So the mass of the first one times the abundance, mass of the second one times its abundance, mass of the third one times its abundance, and so forth. A big tip, though, is make sure you put your percentages into decimal form. We don't want to use 98%, 30%, 42%. Just put it into a decimal, especially in your work and as well as your calculator. It's going to lead to a lot less mistakes. So do yourself a favor, get rid of the percent, and turn your number back into a decimal number. Pretty sure we all know how to go from percent to decimal. Just divide by 100. So here's an example. We'll look at magnesium. We have 3 masses of magnesium as well as their abundance converted to a decimal. So I'll take the first one and multiply by its abundance. I'll take the second one, magnesium 25 times its abundance, and the third one, magnesium 26 times its abundance. Add them all up, final step, and you get 24.31. AMU is the units. Later on, it'll be grams per mole. That's a whole nother discussion later on. Now, usually you are given real masses to work with, but in case you're not, just take the mass number. I mean, it's close enough, it works out, it's not going to make your answer incorrect by any stretch of the imagination. Any questions on this calculation? All right, now let's go in reverse. Let's find the abundance. Well, pretty much the same equation we just saw, except we're solving for a different variable. I'm going to let X represent the abundance of the first isotope, and I'm going to use 1 minus X to represent the abundance of the second isotope. This really works well when there's only 2 isotopes, so don't worry about having to do this with more than 2 isotopes in your problem. Clearly, we want 1 minus X because both abundances have to add up to 100%. I mean, that makes sense, right? As it should. And remember, 100% is the same as 1 to make the math easier. So remember to undo a decimal, just divide by 100. and, or sorry, undo a percentage, divide by 100, so makes it easy. So our goal here is to calculate the percent abundance for each isotope if the average atomic mass of boron is 10.81. Well, I know boron has two isotopes. The first one, boron 10, weighs this much. The second isotope, boron 11, weighs this much. Now, before I even start the problem, which of these two boron isotopes should have the larger abundance? Hopefully you said boron 11 because its mass is the closest to the overall average. So it's kind of a way to self-check at the end, because conceptually, before you started the problem, you know the larger abundance should be with boron 11 due to the fact that it's closer to the average. If it's not in your answer, that's a clear indication or a red flag that you've possibly made a mistake and need to recheck your work. So my equation, pretty self-explanatory. Average mass equals mass of isotope times abundance plus mass of isotope times abundance. Plug your numbers in, solve for x, easy enough. We're going to get boron 10 has a value of this, 19.98%. So that's pretty small. Therefore, boron 11 is just 1 minus your x value, and you're left with 80.02%. So clearly, boron 11 has the larger abundance because it's closer to the overall average. Any questions on this type of calculation? Thank you.